Well, Paul's given us a great overview of the messenger mission, very nicely illustrating the history, the how, and the why. Now, I know many of you have been browsing the images posted by NASA on the web, so I asked Brian if I could take a few minutes tonight to briefly highlight the geological significance of what it is you're looking at when you look at those images. And I wanted to do that before the topic goes cold on us. Great. So I hit, which button do I hit?
That one of
There, good. I don't even need to walk away from here. Okay, so let me start with a disclaimer. Almost none of what I'm going to tell you tonight has been described on NASA's website yet, but I'm hoping they're going to. There's text which accompanies these various images, and they're rather superficial, and yet by looking at these images with a geologist's eyes, there are some really exciting things already to be seen. There's one other thing I want to point out to you, and I'll come back to it at the end, and that is, can I just remind you of what MESSENGER stands for? MESSENGER stands for Mercury, Surface, Space, Environment, Geochemistry, and Ranging. And what I want to come back to at the end of the talk is the geochemistry part of it. Okay, next slide, please, Chris. Good. All right, so as Paul's already pointed out, at first glance, depending on where you look on Mercury, the surface of Mercury, seen through MESSENGER's eyes, is rather similar to the Moon. Next one, please, Chris. But elsewhere, on other parts of the planet, there are clear major differences. And some of these were already spotted by that old Mariner probe, and they're extremely nicely illustrated by the new MESSENGER images. So in this image, you can see there are two very different kinds of landscapes. And I'm looking at this area here in the north, and then the rest of it here in the south and the center. And in the north, you can see these old impact craters. You can see them here, here, here. They're pretty large. But the important thing is they're separated from each other by an extremely rough-looking surface. This thing here looks like a file. And it's characterized by what I'd refer to as heavy pockmarking. And in contrast, the central and the southern parts of the image show extensive, shapeless, and that's important, smooth region, which is made of volcanic lava, and it's cut by smaller and fewer impact craters. But you can also see that the lava plains have flooded and drowned these older, larger impact craters here, compared with these other ones here, which are still exposed. So these two features are very different from what you see on Earth's moon, because on the Earth's moon, these pockmarks are actually quite rare. And where you do get extensive lava plains, because you can see them with the naked eye when you look up at the sky at night, you can see with the full moon those dark patches, those are extensive smooth lava plains, but they're confined, they're not shapeless. They're confined to the interiors of well-defined, more or less circular, giant impact basins. Next one, please, Chris. So here's a more detailed MESSENGER image that shows a large crater, and I mean this one here, plus its other smaller ones around, but that's the one I'm referring to. And it's surrounded by this pockmarked terrain. You can see the pockmarked terrain within the area that I'm referring to here. That's all pockmarked. And you notice these radial crater chains. There's a really nice one there. It's a chain of craters. There's another one up there, and there's another one right there. You see how they're radiating away from the center of the crater there. So those crater chains, those were formed by debris ejected from the impact crater. And this tells us, because of their association, spatial association with the pockmarking, that the pockmarks also represent locally derived debris that was tossed up above the impact site and then fell back to the planetary surface very close to the impact crater. Now, this is very different to the behavior of impact debris on the Earth's moon, that is ejected so far that it can fly halfway around the moon before it lands. And you've all seen this kind of thing. When you look up at the full moon, for example, you've seen those bright rays that we see extending from the crater Tycho in the moon's southern hemisphere. And you know from just looking at them, even with the naked eye, they practically go halfway around the moon. So why the difference between the moon and Mercury in terms of these cratering mechanics, if you will? It all comes down to gravity. As Paul pointed out, Mercury is about 40% the size of the Earth, but because it has an unusually large nickel-iron core, and nickel and iron are extremely dense, its average density is about the same as that of the Earth, all of which adds up to about 40% of the Earth's gravity. But the Moon, at about 25% the size of the Earth, with a very small nickel-iron core, it has less than 25% of the Earth's gravity. So in simple terms, the impact debris doesn't fly as far on Mercury as it does on the Moon. Next one, please, Chris. So this picture here summarizes the essential features of impact features commonly present on Mercury as seen by MESSENGER. And there are three things to note here. One, the first thing is this double ring crater. There's an inside ring, and there's the outer ring of that crater. Now, these double ring craters, they do occur on the Moon, but they're much more common on Mercury, and they're smaller on Mercury than they are on the Moon. And again, this is a function of Mercury's greater gravity. And in a nutshell, the reason these rings in here form really comes down to the way that the material falls back into the hole when the crater formed in the first place and starts coming in from the outer parts of the crater in towards the interior. And that's where that second ring there forms. So you can see that if material's falling back into a hole, gravity will have an influence. Secondly, in the immediate vicinity of the impact crater is that pockmarked area. See all the pockmarks to the right of a line like this. See all the pockmarking. And that, of course, is derived from the impact ejecta, as I say, associated with these radial secondary impact crater chains. There's one beautiful one there. There's another one out there. And there are several others coming up. There's one right there. And it just so happens that the third feature of this image is that in contrast to the MESSENGER image I showed you previously, where the lavas were actually drowning old craters, here the impact and pockmarking is clearly younger than the smooth volcanic plains here to the left of the image. You can see that even the radial crater chains are affecting the smooth lava plains. And because the major phase of impact cratering throughout the solar system is associated with the Great Bombardment that ended 3.8 billion, that's billion not million, 3.8 billion years ago, the presence of smooth lavas that drown older craters but are also heavily impacted by younger ones, as in this image, that tells us that the lavas themselves probably formed at about 3.8 billion years ago as well. And this highlights another difference with Earth's Moon, where on the Moon, the lavas that filled up the giant impact basins are hundreds of millions of years younger than the end of the Great Bombardment. Next one, please, Chris. Okay, now these two are not MESSENGER images. They were taken by Mariner over 30 years ago. When Mercury cooled soon after its formation, the oversized iron-nickel core in its interior shrank because the temperature was going down, and that forced the surface of the planet to shrink with it. And that led to the formation of what are called contraction ridges. They're hundreds of kilometers long, and they're a feature that's truly unique in the solar system. You can see them here. There's one of these fractures here. Here's a close-up of it, exactly the same fracture. And the point of this image here is you can see the curvature of the horizon of Mercury, and that shows you just how big that fracture must be. Well, that fracture, as I said, is due to contraction. And if we go to the next slide, this is a MESSENGER image. It's an incredibly detailed MESSENGER image of a section of one of these contraction ridges. And if you look very carefully, you can see how the planetary crust on the right, here's the section of contraction ridge. And the planetary crust on the right here has moved westwards over the crust on the left here. And what it's done is it's partially buried. Look at this crater right there. It's partially buried it. It's no longer circular. Its southeastern corner is actually overlapped by this material moving up and over this material here. So you can literally see how the mercurial crust moved during the planetary contraction with this incredible MESSENGER image. Next one, please, Chris. Now, this is my last MESSENGER image for tonight. And this is one that NASA is making a lot of fuss about. And I'm going to tell you, I'm afraid it's a rather unnecessary fuss. In typical NASA fashion, they call it the spider. And they associate it with the crater that you can see near the center. Now, what they're pointing at here, of course, are these radial fractures here, going out around 360 degrees, I guess rather like the legs of a spider, if you will. But if the impact crater was really associated with these radial cracks, then it might indeed be a unique feature in the solar system, as NASA claims. Next one, please, Chris. But if you look, it's nothing of the kind. The crater itself is clearly off-center with respect to the radiating features, and it's clearly a late feature that formed after the radial fractures. So, okay, let's now look at this through geological eyes. Okay, we'll look at it through my eyes. Now, if you look carefully in the south of the image, look at this fracture feature right there. That's not a little crack. That's actually a fracture with a finite width to it, and you can see that it's actually a narrow rift valley. A rift valley rather like the Ottawa Valley is a rift valley, where the flat floor of the valley floor has actually dropped down with respect to the walls on either side. And if you look carefully, you can now see that this is the case for all of these fractures. Even these narrow ones here, 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 they're the same kind of thing. They're the valley floors which are flat and have dropped down with respect to the shoulders on either side. This is a very common feature on Earth. I was taught about this as a student more years ago than I care to remember. These radiating mini rift valleys represent a failed volcano, albeit a big one here on Mercury. There's the scale bar, so this is hundreds of kilometers across. It was going to be a rather large volcano had it formed. The way this forms is that lava, or molten rock, rose as a narrow plume from the planetary interior. We're talking Mercury here, remember. But it did not reach the surface. So it pushed up the planetary surface, which then cracked radially as it bulged and stretched. Now the lava ran out radially along these cracks, and as it cooled and crystallized to form solid rock, it shrank because the temperature was going down. So as the ejected lava shrank, the roof of rock above the vertical lava sheet dropped down to form these mini rift valleys, the best one of which, of course, you can see right there. Now, the important point here is that this is a very common feature on Earth, and in fact, one of the best examples is known from New Mexico in the southern United States. It's somewhat smaller than this, but not that much. Now, let me just come back to this business of geochemistry. One of the things that we've not heard about from NASA regarding the Messenger flyby is anything about the chemistry of the surface of the planet. And this is extremely important because there are a number of theories to explain why it is that such a small planet like Mercury has such a large, dense core relative to its size. And all of them essentially suggest, or at least two of the major ones suggest, that one way or the other, either due to a collision or early in the history of the Sun, because Mercury was in so close, the outer layers of Mercury were blown away. And so the outer layers were stripped off, the core remained, and the remaining non-core material forms the outer part of the planet. Now, when Mariner went by, it too thought it could recognize the geochemistry of Mercury, and it thought it was made of a rock called anorthosite, which I won't get into the technical details of, but it's exactly the same as the white stuff on the surface of the Moon. In other words, it's exactly what you would expect to see on the outer surface of a rocky planet in its primitive state. So if it is, in fact, anorthosite that forms the outer part of Mercury, then these theories of accounting for the large dense core of Mercury by blowing away the outer layers cannot work, because the composition would have to be something different from anorthosite. The interesting thing is that we know that all of the instruments were operating on Messenger, but the one thing we haven't heard anything about from NASA is the chemical composition of the surface of Mercury. Now, I'm not the only person that's noticed that. By the way, if you follow things like Astronomy Magazine and their webpage, then one of their columnists has also raised this as well, and is wondering what it is that NASA is hiding from us. Well, let's hope we'll find out in the next month or so, because it's going to be very interesting when we actually get that result. So my take-home message tonight is this. Number one, Messenger has sent us back some wonderfully detailed images. Number two, geologically speaking, there's nothing new that the old Mariner probe hadn't already shown us except for the spider. But the new images are extraordinarily detailed. And number three, the hidden side of Mercury does not seem to contain any unexpected surprises. So finally, what I'd recommend to you is have fun looking at these new images from Mercury. We know that the next swing by will be in October, and we'll get a new batch of really high-quality images of our enigmatic neighbor. For those of you that are interested in a more detailed geological analysis of what Messenger's already given us, I'm going to be sending a more extensive set of images and text to our RASC web volunteers for inclusion on the articles page when they have the time to process it. Thank you very much for listening.
Way in the back.
Way in the back, Rob?
I was kind of disappointed in Messenger's images because I was kind of looking.
Rob, speak up.
I was rather disappointed in some of the images because I was kind of looking forward to the different terrains that we saw on the Moon, where the near side has got the mare, the back doesn't, and even Mars, the north hemisphere is more
There's a reason for it. There's a reason for it. There are two reasons, in fact, because I noticed the same thing. The very first image, if you notice the way that the images came out on the web, they came out in drips and drabs. It was 1 or 2 images a day. And the very first images were absolutely remarkable, remarkably sharp. And then as the days wore on, they got a little fuzzy and a little fuzzier. And then they started analyzing the crater impact statistics with little green circles and so on, and you couldn't see anything in the image at all. And I suddenly realized what was going on. It's a flyby. They're not in orbit. And so only at a certain range and certain speed could they get really good images. But one of the most remarkable things is that on Mercury is a rather large impact basin. And it's a multi-ring impact basin, rather like another rather large one on the Moon. And Mariner actually took a better picture. It only photographed half of it, but it's a much better picture. In fact, you can't even see this huge multi-ring basin in the messenger images. And I scratched my head on this one for a while, and then somebody, I forget who, stitched 2 of them together, and you could see immediately why. The sun angle. The sun angle for the Mariner images 35 years ago was really low, and so the relief of all the topographic features came out so beautifully. And on this flyby, the sun angle was really high, and you could barely see some of the same craters that Mariner had already seen. So I think that's the reason, Rob. And it's going to be touch and go for the next 2 flybys as to how good the images are. But once that probe settles into a steady orbit around the planet, we're going to see some remarkable images.
I'll just make a note that the large basin to be named later, the spider's right in the middle of it. Isn't that right?
It is, in fact, approximately in the middle, yeah.
Do you think the impact itself had a factor to do with this volcano?
No, not at all. This impact is clearly late. It overprints, it cuts across the rifts.
No, I mean the basin itself.
That is conceivable. That is conceivable, although it's very, very different in scale.
It is.
This is, compared with the impact basin, this is a small volcano. It's a large volcano compared with volcanoes on Earth.
Right. Thank you very much, Simon.